Well, thank you very much for the invitation. So I'll talk today about a concept that we discovered and formulated a few years ago that in materials that we call metadamping. Essentially, what this is the notion of enhanced dissipation. When you have a metamaterial, you in principle you realize an enhancement in dissipation. So we formulate theoretically formulate this concept and also experimentally demonstrate it. So that's what the talk will be about today. But before I start, I just want to take a minute to acknowledge two of my former students, PhD students, who played an important role in this work. Michael Fraser, who's now an assistant professor at UC San Diego, and Clémence Baquet, who is now R&D and engineer in Dassault Aviation in Paris, France. Okay, so let me see if I can flip the slide. So I would like to motivate the idea by showing you this, one of those classical Ashby diagrams. I'm sure you're very familiar with these diagrams. Specifically, I'm showing you one that shows the loss factor coefficient as a function of the Young's modulus. So this is essentially a mapping of all different types of materials, how they relate in terms of their damping capacity on one hand, and their Young's modulus or stiffness, if you will, on the other hand. And clearly you can see that negative line, so that's a trade-off. That's a fundamental trade-off that you have natural materials. So what would be interesting, and you can simplify that. Essentially, metals, as you can see, are typically stiff, but don't exhibit that much dissipation. On the other hand, polymers, they are highly damped materials in general, but not necessarily very stiff. So if you want load-bearing capacity, but also damping, you really want to enter into this uncharted territory here, which is the white space. So you want to break that fundamental barrier and enter into this region. So what we're going to show today is that with careful design, you can actually achieve that with metamaterials. So we will start with a metal, for example, a normal metal, and show that by some certain substructuring, essentially introducing resonances, we can enter into this region and go into that white space. So in fact, that whole white space I'd like to call metaspace. So this is the space that is unnatural that we can enter. So I'm going to talk, describe the concept, give you some examples and so on. But if you're interested in going deeper into the idea of metadamping, this is the original paper that we got out back in 2013, metadamping and immersion phenomenon, dissipative metamaterials. Okay, but before I get into this, I just want to quickly underline a key distinction it's quite simple, but often overlooked, at least in terms of terminology. I want to distinguish between damping and dissipation. So when we talk about material properties, we talk about density, stiffness, and we can talk about prescribed damping in the same way. On the other hand, when we look at the response, for example, the response of a structured material, then we refer to the natural frequency or natural frequencies, and also to the dissipation. So damping and dissipation, at least in my talk, have different meanings. Damping is something that we prescribe. The dissipation is something that emerges from the response. So with that in mind, so we can look at an actual structure, for example, this beam here, which we can model by finite elements, let's say, and we can introduce a damping matrix. For simplicity, we'll just use Rayleigh damping, which is proportional to mass stiffness. We can experimentally get an FRF also numerically, and by model analysis, we can extract the damping ratio for each mode. So you can see here these two damping ratios obtained. So based on that terminology, then our choice of P and Q, which are the proportionality constants for defining the damping, are going to be the prescribed damping. And then on the other hand, the actual response, how much damping ratio each mode exhibits, will be the dissipation. So that's the distinction here. All right, so with this background in mind, the goal is essentially to utilize locally resonant metamaterials to control, and by control I mean maximize or even minimize the dissipation over a broad frequency range. So engineering of loss, if you'd like, using metamaterials. So I have 3 points in my outline that I would like to go over. One is just a quick introduction, and it's important to properly In order to properly introduce the notion of metadamping, it's important to introduce the basic ideas of phononic materials, whether elastic metamaterials or phononic crystals. And then I'm going to talk about the treatment of damping in phononic materials, and then move on to the main topic, which is metadamping. Okay, so what's a phononic material in general? So a phononic material is a structured material, usually periodic, that admits phonons. So of course, phonons fundamentally is a concept that resides in quantum mechanics, quanta of mechanical vibrations. But over time, informally, it has expanded in scope. And now when we talk about phonons or phonon-related phenomena in a variety of disciplines, whether it's elastic waves, acoustics, heat, and so on. So in this context, there's two types or two classes, phononic crystals and metamaterials. I'm showing examples here, 1D, 2D, and 3D. The key difference is that in a phononic crystal, the basic mechanism for creating the interesting wave propagation properties is Bragg scattering, wave interferences. In metamaterials, on the other hand, it's resonances. You can have periodicity as well for convenience and for analysis, but the key idea is resonances. And I'm showing here at the bottom left that well-recognized model that came out of the seminal paper from Ping Sheng's group in 2000 that shows you inclusions with a compliant coating. So essentially that inclusion acts as a resonator. It can also, this concept can be realized in terms of a plate with pillars, so the pillars can act as resonators and different other forms. And since then, there's been an abundance of applications. So wave guiding, acoustic cloaking, we heard the first talk today about seismic cloaking, focusing, and from our own group, passive wave propagation based on phonons. So there's plenty of applications, and there's a review article here down there I'm referencing from 2014, where we essentially survey the whole field historically and as well as contemporary achievements. Okay, so I want to just take a minute and just highlight the key wave propagation class. So I'm going to take the simplest case in each case, the 1D for the phononic crystal, as well as the 1D for the metamaterial. So for a phononic crystal, if we plot the dispersion diagram, frequency versus wave number, and we plot, let's say, the first two branches, and we can see a band gap, that's a Bragg scattering band gap. Then if we look at a corresponding 1D metamaterial with pillars, we'll also see a band gap, but this band gap is fundamentally different. It's a local resonance band gap. It gets realized due to a hybridization between the resonant mode that we're looking at specifically here and its coupling with the underlying dispersion. So essentially this means that the band gap can be in the subwavelength regime, and it doesn't necessarily actually depend on periodicity. So you can contrast the two clearly in this picture. Okay, so now let me talk a little about how we treat damping and some subtle features when we talk about damping in phononic materials. Specifically, I want to highlight two distinct problems that sometimes are often mixed in the field. One is the notion of free propagating waves, wave number dependent free propagating waves, and the other is wave number dependent driven waves. If you plot the dispersion diagram for both those types of waves, they're essentially identical without damping. However, once you add damping, the dispersion diagrams themselves start to change because of whether we are freely allowing the waves to propagate or driving them with a prescribed frequency. So in the first class, typically, not necessarily though, you fix a real wave number, you get the complex frequencies. So what you get is dissipation in time. So your attenuation is in time. So there's been several papers, including some of ours, that focus on this specific class of problems. On the other hand, perhaps more common is when you fix a real frequency. So you introduce, by restriction, the frequency has to be real. So that's why we call it driven waves. And then you calculate the complex wave numbers. So there, the dissipation is only in space. There's no dissipation in time. It's a steady state problem. And there's been a lot of papers in that area as well. I quickly want to mention that, in fact, for the first class of problem, while it's convenient to fix the wave number to be real, in principle, it can be complex. Both the wave number and frequency is complex. And we described that in this paper here in 2016. Okay, so I just want to demonstrate the implication of this very quickly before I get into metadamping. So using a very simple spring mass system, I'm not going to go into the math, but that's a straightforward problem. We apply Bloch's theorem, and note here, if we're looking at free waves, the frequency is complex, lambda. So when we obtain the characteristic equation and solve it, essentially we have two parts, a real part and an imaginary part. From the imaginary part, we get the damped frequencies. From the real part, we can get that dissipation, the wave number dependent damping ratio. And then there's omega s, which is the resonant frequency, which in the case of proportional damping is equal to the undamped frequency. So that's the basic picture for free waves. So let's see how it manifests. So this is a dispersion diagram. On the left, this frequency, on the right, damping ratio. No damping at all so far. Now let's add a little bit of damping and see what happens to the dispersion dropping. And then on the right-hand side, we can quantify that amount of dissipation using this damping ratio concept. So you can see each branch has its corresponding dissipation. And then when we add more damping, we get further dissipation and more dropping in the dispersion and so on, until we reach the point where we can start having overdamped in some of the waves in the billion zone. In contrast, if we look at the harmonically driven problem, the other type of problem, there, and that's the one that's more common, there, the frequency is real, as I said. So lambda is set to be equal to I omega. So typically we solve this problem as a frequency, as a wave number as a function of frequency, whereby essentially we get propagating modes and attenuating modes. But as I explained before, these attenuating modes will be in space, not in time. So let's see how that in turn manifests in the dispersion. So that's exactly the same dispersion that I showed you before for the free waves without damping. But now when we add damping, look what happens. Something totally different emerges. The dispersion looks different. In fact, the gap closes, that's the part, the imaginary part, and then as we add more damping, this effect intensifies. So if you contrast them, even though they're identical systems, but under free waves and under harmonically driven waves, the dispersion is different when we add damping. And in the case of free waves, we can quantify the temporal dissipation. In the case of harmonically driven waves, we can essentially naturally quantify the spatial attenuation in the imaginary wave number space. Okay, so my treatment of metadamping that I'll show you shortly now lies in the free waves side of those two classes of problems. Okay, so now with that background as well in place, let me now get into the main topic, which is metadamping, engineering dissipation with metamaterials. Remember the diagram that I showed you, this motivational diagram that I showed you earlier? What I'll do now for the rest of the talk is physically demonstrate how we can actually do that, how we can realize this concept of metadamping. And we'll show it theoretically as well as experimentally. So I'm gonna do this again, resorting just to start with, always easy to start with simple models. So we're gonna start with this widely used mass and mass model shown there on the right. So this is a periodic chain. And you can see the dispersion diagram down there. And then what I'll do, and this is where in the title of the talk, I mentioned static equivalence. So now what I'll do in order to quantify the notion of metadamping, let alone understanding, I'm going to consider a statically equivalent phononic crystal. So this phononic crystal on the left has exactly the same total mass as the metamaterial. They both weigh the same, have exactly the same amount of prescribed damping. The dash plots are identical. And in the static limit, they statically deform identically. So they are identical materials statically. And you can see this from the slope of the dispersion curves in the long wave limit. The speed of sound for both is identical. Except when we start adding frequency, this is when they differ because of the resonances. So then, as I explained before, we can plot the damping ratio diagrams, the dissipation, and here's the interesting part. We can see how the dissipation mechanism in a metamaterial differs from a corresponding phononic crystal. So you can clearly see that the dissipation actually increases. And that, in fact, is what we call metadamping. And this increase in dissipation, or this emergence of dissipation, is inherent in the system. It's an intrinsic property. It spans the whole Brillouin zone. So we can take a step further and quantify it by integrating that dissipation over the Brillouin zone and some over the branches, get a total zeta quantity, and then plot that versus that long wave speed of sound, which is a measure of stiffness, and essentially reproduce this ambitious picture that I started with earlier. So let's see how it looks like. Basically, if I then plot that total dissipation metric versus the speed of sound, which is a representation of stiffness, you'll see here this solid red line. That line is for the phononic crystal. Then the dashed red line is for the metamaterial. And you can see that we've essentially increased the dissipation, and by that amount of gray area. So if we plot it in a log scale, we recover identically that idealistic scenario that we were aiming. And we did that just simply by adding a resonator into a material, not doing anything else. So that's yet another element of the magic of metamaterials, not just from the point of view of band gaps and effective properties and cloaking and so on, but also from the point of view of dissipation. Since then, a few works have emerged that takes this concept and applies it in for different type of metamaterial systems. So for example, this group from Greece have considered negative stiffness, and they demonstrated the metadamping as shown by this blue arrow there. And then the Mustafa Nuh group in Buffalo have examined this idea of linking the resonators together in a metamaterial, which they call a phononic resonator. And they've considered similar analysis to what we've done to quantify the metadamping. And this is on the left here is for a certain set of parameters, and then on the right there for another set. Let's look at the right case. Basically, the first column is the dispersion and dissipation for that benchmark phononic crystal. Then you can see when you turn this into a metamaterial by mass and mass, the dissipation increases by that much, so you get this much metadamping. And then when you add that feature of linking the resonators, you add even further dissipation. So it's really interesting, showing how by manipulating the inner dynamics of a material, a metamaterial, without changing the general properties, total mass, prescribed damping, and so on, for equivalently static systems, you're totally changing the dissipation capacity, the damping capacity of the material. All right, so for the remaining part of the talk, I want to show you how this extends to actual experimental system. So we're going to take a beam with pillars. So that will be our metamaterial, experimental and numerical. And then, as always, we have to compare with a benchmark to quantify the emergence of dissipation. So we'll compare with an unpillared beam. So for that model, I'm not going to get into the modeling details, but you'll see on the left here for the unpillared beam, the dispersion diagram. It's more complex, of course, because even though it's 1D wave propagation, it's a 3D elastic model. And then on the right, we have the damping ratio diagram. Then we can superimpose the metamaterials, which was by adding that pillar. And we've designed it such that the two extreme branches in the long wave limit are identical for both systems. So you can see that the speed of sound for the flexural mode and the longitudinal mode are identical. So in this manner, we can resemble what we've done before and quantify the metadamping by comparing those two systems. So we do this as follows. We basically zoom into an area where there's a resonance or a couple of resonances and show the dispersion diagram on the one hand and then the damping ratio diagram. And let's zoom in further. And here we're showing this color contour is essentially a representation of how much of each mode has longitudinal motion versus shear motion. So it's just an additional feature. But what is important here is that if you look at that straight line here, that's the unpillared case. And then these curved lines is for the pillared case. And then correspondingly, that's the damping ratio. So by adding that pillar for that identical beam, by simply adding the pillar, you'll see that that straight line in the dispersion has turned into this curved line. And correspondingly, that curved dissipation line has increased by that much. And that, in fact, is a quantification of our dissipation. So here we have technically observed a metadamping. And now, how do we test it? Now, ideally, of course, we could test it in a wave propagation setting, but that's not very easy. So more simply and also more practically, we can just test it in the context of simple vibration, impulse type testing. So we take that beam here with the pillars, we excite it with an impulse function. So that impulse function is engineered to be identical for both the pillar and unpillared case for fairness. And what we're showing here is the attenuation with time. So the acceleration versus time and you can see that the pillared problem has stronger attenuation than the unpillared. Remember, this is attenuation in time, not in space. So this is not the band gap phenomena. This is the metadamping phenomena. It's very different. And we showed qualitatively the same result by numerical simulations. So interestingly enough, not only we can demonstrate this, we can demonstrate positive metadamping. In fact, we can also demonstrate negative metadamping. Let me quickly show you how. So in this case, our impulse function, if we look at its spectral content, it matched the region where the original curve of the unpillared turns into that curve, which corresponds to an increase in dissipation. But if alternatively, we excite with a different signal impulse that has a frequency content that is slightly shifted upwards, matching that region here, well, in that case, the original line will drop rather than increase. And by doing that, we're effectively realizing negative metadamping. So we're reducing the loss. So we can engineer the dissipation just exactly how we want by engineering the system according to the spectrum of excitation we have for our problem. So that was it for me. I want to quickly summarize the idea of metadamping. So we've introduced it. It's basically one way to look at it is an emergence of dissipation, which you can engineer using metamaterials. We validated that concept in a finite experimental setting with direct correlation to the theory of metadamping as described, as I showed you in the dispersion framework, using the dispersion as well as the damping ratio diagrams. Ongoing work, there's several. One of them we're extending to 2D in collaboration with our colleagues in Tianjin in China. And in addition to that original paper that I showed you earlier, the 2013 paper, you can learn more about the concept in a review article that just appeared a couple of years ago in Advances in Applied Mechanics. So that's all what I had for today, and I'm happy to answer any questions for you.